So, acceleration.
Acceleration.
Today we're going to talk about acceleration. When you think of acceleration, what do you think of? A car going forward. What do you think of?
Something going fast.
Something going fast. Yes.
From nothing to something really fast.
Nothing to something really fast.
An aeroplane coming off the runway.
Coming off the runway. So, we have things that are going from nothing to going really fast. We have cars, because they even have things called accelerators, right? So we're thinking of vehicles and things that are going fast.
I'm thinking SU.
So, yes, it really does have things with going fast, but not always. That's not what you think of. It's really weird if you think of that. No one thinks of that. Yeah, I looked in the book. See, you didn't think of it. The book thought of it. So, going fast. Acceleration is the rate of change in speed. However, it's not just the rate of change in speed. Because you guys talk about, starting at nothing and going to something, right?
Yes.
But it's not just speed. No. Acceleration is rate of change in velocity. And when you include velocity is different than speed, Henderson. Do you remember how?
It has quantity.
Yes, a specific quantity. Yes?
Direction.
Which is direction. Right. So, so you're thinking of the vector. A vector is a quantity with direction. Right. Exactly right. So, rate of change in velocity, which is a vector, is acceleration. So that means, since the change in velocity is acceleration and velocity has a direction, therefore, acceleration is also a vector, by definition. Yes, sir?
Would not the velocity change have to be an increase in velocity?
Negative. In fact, it could be positive or negative. So, if you have a positive acceleration, we call it acceleration. And if we have a negative acceleration, we call it deceleration. So, you could say 5 meters per second squared. You could say negative 5 meters per second squared. Yes? And we know that one is increasing velocity, one is decreasing velocity. They are both forms of acceleration. A negative acceleration is a deceleration. Now, there's one more missing. So we have positive, so we're going faster. Negative, we're going slower. And then we have the other one. What's the other one?
Neutral.
We don't have to change speed to change acceleration.
No.
We can change direction. That's the third one.
Woohoo!
Right? So Mr. Schuth is standing in place. When I turn direction, I'm actually accelerating. How about that? Let's do it even worse. Let's do this. Let's say Mr. Shoes creates a merry-go-round. He's done doing Pop-Tarts, now he's doing a merry-go-round, and kids come to him with their extra money, and they get on the merry-go-round, and he's made little horsies.
The merry-go-round's better than your state of Indiana.
See, a little horsey with the... And, they always have those benches, right? Okay. And it goes around and around and around. Now, let's say... Yeah. We had a distance time graph going, and we started up, and it starts going faster, until it gets to a constant speed, yes? So it's going to this constant speed, and it's going around, around, around. So what is acceleration? Yes?
The velocity in which the carousel...
Would you say there's any acceleration going on right in here, where it's constant speed?
No, because it's constant.
See, it's constant speed. However, it's constantly changing directions. So therefore, it is constantly accelerating.
How so?
By definition, because, let's go back. Because acceleration is a change in velocity. Velocity has direction. So, since we're constantly changing direction, even though our speed is the same, it's a constant speed with a constant acceleration.
Indubitably.
Oh, that's the tricky one for acceleration. So let's get back to not so tricky. Right? So, if it's a rate of change in velocity, you simply take the final velocity minus the initial velocity, and it's the rate, so it's divided by time. How fast does your velocity change?
What's A?
So A is acceleration, VF is final velocity, VI is initial velocity, and T is time. Right? So since velocity is meters per second and time is measured in... What's time measured in? Seconds, it's meters per second per second. Uh-oh. Now you're starting to see what I meant by foundations, right?
Yes.
Yesterday we did distance, and then we added time to it, rate of change of distance, or how fast does distance change? That's speed. And then we say, well, how fast does speed change? And so we're adding yet another little unit. Now, if you wanted to, you could say that meters per second over seconds is meters over seconds over 1. And so you could say, well, let's multiply by 1 over seconds on both the top and the bottom, and that factors out, and you're left with meters per second squared. You might have heard that before.
So acceleration.
So this
S over S.
meters per second squared equals meters per second. Right? So you can simplify it that way, meters per second squared, you'll see it a lot, or you can have it meters per second. Either way, it's the same thing.
Does it matter?
It doesn't matter which one you use, so long as it makes sense to you. Use the one that makes sense to you. Okay? Alright, so let's do a practice problem, shall we? Let's say, aha! Let's say 90. 90 has started to smell the cinnamon rolls on breakfast for lunch day. And she starts running down the hallway. Oh, wait. No, that's not. You got a ponytail today. Okay. It's a headband or something. Okay. So she starts out of her seat. She started at 0 meters per second, but she ends up going 20 meters per second because she really likes those cinnamon rolls. And she's very inspired. It only takes her, let's say, 5 seconds to do this. So the question is, what's the acceleration? And so we say, Mr. Schuth, we know how to do this. We're going to write the formula. So A equals BF minus BI over time, right? Well, what's her final velocity?
20 meters.
It was 20 meters per second, right? What's her initial velocity?
0.
0 makes it easy, doesn't it? She wasn't going anywhere to begin with, and how long did it take her?
5 seconds.
5 seconds to do the acceleration. So what's 20 divided by 5?
4.
4. And that's 4 meters per second per second. Or you could say it's 4 meters per second squared. So what that means is every second that went by, on average, she accelerated by 4 meters per second. So at 1 second, she's going 4 meters a second. At 2 seconds, how fast is she going?
8.
8 meters per second. So she's going faster and faster and faster. Right?
Yeah.
Okay. So this is rate of change in
20
speed.
divided by 5.
Every second that goes by, she's going 4 meters per second faster. Now, what would happen on the other hand? So here we have 90, right? And we know she's booking it. Alright? I don't know how to do this other one here. Looks like she's more like flying here. Okay.
If she's falling.
Alright. So she's going at 20 meters a second now, right? Uh-oh. But then we run into trouble. Miss McDougal. Right? That's a silly nose, isn't it?
I can't see.
Miss McDougal. Right? And she's got her little hand here. 1, 2, 3, 4, 5. Right? And over here, she's waving the orange cone. She sees someone running, and 90 says, no. Right? And so she slows down to 0 meters per second, but she doesn't see Miss McDougal in time. It takes her, let's say, 10 seconds to slow down. Because she's sitting there going by. And then finally looks and, oh no.
How far is...
Doesn't want to look like she's running, but...
How far are those two from each other?
So, let's find out her acceleration. So acceleration, Mr. Schuth, I know how to do this. I'm going to write the formula.
It's actually decelerating.
So final velocity minus initial velocity over time. So final velocity was?
0.
0 meters per second. Initial velocity was?
20.
20 meters per second. Oh, golly. And her time?
10 seconds.
10 seconds. Oh, 90.
-2. Silly.
So look at this. What is negative 20? What's 0 minus 20?
Negative 20.
Negative 20. What's negative 20 divided by 10?
-2
Negative
meters
2.
per second squared.
Negative 2 meters per second squared. So, her deceleration is 2 meters per second squared, or her acceleration is negative 2 meters per second squared.
So how far is she from Miss McDougal?
Not far enough. Yes, if you still able to hand her that. Right? Does that make sense?
How
So, let's take a look at this graphically. Yesterday, we talked about distance versus time, right? And if you have distance versus time, let's say it looks like this. What does that mean?
Constant time. Oh no,
You're doing
the
nothing.
distance is
Distance is nothing. You're not going anywhere, right?
Yeah.
Now, on the other hand, what would this be?
Means you're
You are
going
not at a
It's
constant
a constant speed, right? We're okay with that. What about, on the other hand, distance time? What if it looks like that?
That means going slow and nowhere, and then you go really fast.
So you're accelerating, right? You're going faster. So you're going greater distance in the same amount of time. Okay, now let's do a little fancier one. Ready? We're going to do speed versus time. Straight line on a speed versus time.
Constant speed.
Constant speed, right? Same speed the whole time. All right, what about this one? What's that?
You're
Constantly
accelerating.
Constant acceleration. Your speed is increasing at a constant rate. So this is constant acceleration, right? What about, what about that one?
That means you're
Constant
constantly
deceleration.
Constantly decelerating.
until 0.
Okay, now what about this one?
Non-constant.
You are accelerating, right? But it's not constant.
You accelerate.
Your acceleration is actually increasing over time, right? And so for something like this, you would say, you'd have to pick a point, draw a line tangent to the curve, and say that is your instantaneous acceleration at that point. Bam. That's how speedometers work, right? They show your speed at that instant. They're not showing your actual acceleration. Make sense? Now, when you use the brakes on a car, you are also accelerating, except it is a negative acceleration. Deceleration. Okay?
So you're always accelerating.
Yeah, always accelerating. Yeah, Questions on that? No? I think that's about it for acceleration. The tricky part is that you just have a new unit. And so, Mr. Schuth could say, okay, let's say Mr. Schuth drops an egg from the top of the gym. And it has an acceleration of 10 meters per second towards the ground. Yes?
Yes.
Now the final velocity is going to be 0 meters per second, or meters per second, yep. The initial, no, I'm sorry. So let's say the final velocity is going to be 30 meters per second. And the initial velocity was what? 0 meters per second. So the question is, how long is it going to take? And so if your initial formula is going to look like this, then what do you have to solve for? You have to solve for time. You need time by itself. You say that time, so it's going to be VF minus VI all over A, right? Right? So your final velocity was 30 meters per second. Your initial velocity was 0 meters per second. And the acceleration was 10 meters per second squared. So 30 divided by 10 is? 3. And what are the units? Well, meter per second divided by meter per second squared leaves? 1 over S, which is seconds. 3 seconds. Right? Now, it's even worse. Because if you wanted to, you could ask a different question and ask about what's your initial velocity, what's your final velocity. And then you have to solve for that, and then you have to do addition, subtraction, everything like that.
So it's pretty much math.
Yeah, it's just fairly mathy.
Yay!